Their operating currents are like 10 amps, maybe less, 5 or 6 amps. This is, so from an engineering perspective, a lot of appliances and a lot of things with electric motors have to be able to handle peak currents of pretty high. But this also explains some other things. Like when I was a kid, up in my dad, I was raised on a farm, so we always had tools everywhere in sheds, and there's always something to fix because cows tear up everything. So my dad would be working on something, and I'd be helping him by drilling something. And my dad's old school, but I think just within the past 5 years, he's bought a cordless drill. Like everything had cords on it. You gotta have those. So I'd be using a drill, and if you ever used a drill, especially if you're a kid, you don't really know what you're doing, you try to shut too hard, sometimes your drill bit can get stuck, and you're sitting there pulling the trigger, and the drill bit's not turning. My dad would always say, "Hey, let it go, you're gonna burn up the motor." And I was like, what is he talking about? He was absolutely right, and this is why. Because operational parameters dictate that a drill can only handle so much current. But when you first pull it, before that motor has had a chance to ramp up, and it's just a very small instant of time, it draws a heck of a lot more current than its operating current. It's fine because it's really a true peak. It gets to speed almost immediately. But if your drill bit gets stuck and you're sitting there pulling on the trigger, feeding current into it, then the current that it's drawing just shoots up astronomically, right? A large current produces large temperatures, and you actually will burn up the motor. It doesn't really catch on fire, although some things in it could. You will exceed operational parameters of your equipment really quickly. So it's really important if you have something electronic that's supposed to be rotating and it's not, turn it off until you can figure out what's catching it, right? Because the current just goes up like crazy. Because in real life, you can't get away from this effect. So appliances and tools and things of that nature are designed with this in mind. They're designed to handle the peak currents that are going to come where their operational currents are much, much, much lower than that. Okay. So that's back EMF. It's not really super complicated mathematically, but you need to understand why it happens. It just happens because you have a coil turning in a magnetic field. Even though you made the coil turn by turning the switch on, you still get this effect. Nature's always fighting back and forth with it. Any questions about this? All right. That is back in. All right, so from the practical, let's move to the esoteric. All right. Got to talk about, conceptually, some differences between these induced fields and the fields that we've already studied. So one of the things I said about the electric field was that it's a conservative field. Somebody tell me what that means, please. You're on the right track. Yeah, so specifically starting meaning what? The path. Yeah, there's a path involved. But what are we talking about? So if I were to ask you, how much work do I do against gravity to lift my keys, move them around, and put them right back where I got them? How much work did I do? Total work against gravity was 0, right? Because gravity is another conservative. Gravity is a conservative field. It leads to a conservative force, the field of gravity, the force of gravity. Different things, but really related. And we all learned in Physics 1 to calculate that work done is mgh, right? Really, it's mg delta y, because h, potential energy, is only meaningful when you talk about the difference between 2 points, right? So h always means you're measuring something from 0. But in this case, h turns out to be 0 itself, because I ended and began in the same place. That's the definition of a conservative field. The work done moving along a closed path is equal to 0, right? I can say that mathematically like this. The work done is this, right? This is the calculus form of F delta x. But along a closed path is this, right? We saw that vector notation, that integral notation when we did Gauss's law, when we did Ampere's law. That's what the little circle means. It means that it's a definite integral from A to A, right? I'm just getting back to where I started from. So, for a field to be conservative, this is 0. This is what boils down to MGH, if you want to. So, for the fields we looked at in the first part of the class, this was true. You can talk about the work done by an electric field. No big deal. But if you get back to your starting point, it had to be 0. Okay. Now, if we're this is a general result for conservative fields. But for electrical fields, would you agree that that's the same thing? What is this? This is an electric field into which I have placed a charge. And this then is the force exerted on that charge. We've got to go back to the first part of the semester for this. I get that. Like, this is the electrical force. Some charge times the electrical field E into which you put it. Right? So if the electrical field is truly conservative, this is true. Like, all I did was replace force by the specific example of force. Okay. Well, for the specific cases that a charge is invariable, in other words, the charge is not a function of time, there's not a charge in the process going on, or the charge is just a constant, I can pull it out, no big deal. That should still be 0, right? All I've done so far is do a little bit of math and a little bit of physics, but now let me do a little mathematical sorcery. This is a product, right? The product of that term times that term. For a product to be 0, well, y'all tell me, how can a product be 0?
One has to be 0.
One or both of the terms have to be 0, right? That's the only way a product can be 0. Well, if Q is 0, this is a very uninteresting situation. I mean, it's possible. We're not going to deal with that. So let's assume, for the sake of argument, that we're not dealing with 0 charge, which means for this to be true, this has to be true. In other words, this follows directly from saying that the electric field is conservative. If the electric field is conservative, this quantity is 0. That's a different. I wrote something different than F dot D here. This is the definition of conservative. The work done is 0, but for the specific case of an electrical field, that's this boils down to that. So if the electrical field is conservative, this has to be true. All right. What is in parentheses? We didn't do a whole lot with this, but it's there. What is the term in parentheses? What is E dot dr? It's not energy, but it's related to it. We didn't do a whole lot of this, it's okay. But this is the integral form of this equation. Right? This equation relates a voltage to an electrical field. This is the differential form, this is the integral form. What's in parentheses is a voltage. An electric field integrated over a particular path is a voltage. Right? So, what I have here, this is an expression for a voltage. Okay? Fair enough. Now, if this is an expression for a voltage, that means I can write this down. Right? So, different equations. This is the conservative, this is what comes out of the conservative field equation. This is just saying, this is recognizing that what's in parentheses is a voltage. It has units of voltage. This is a voltage. Okay? Well, what if I'm speaking specifically of an induced EMF? Anybody see a problem? There's no guarantee that this is 0. In fact, all the problems we've done for the past 2 days, this is definitely not 0. what is going on, right? And so let's just sum up. This is true if the electric field is conservative. Has to be true, by definition. This is true. The outer portions of this equation are true for induced EMFs. But induced EMFs are just EMFs. They produce electric fields. And if I integrate the electric field produced by the induced EMF over some path, that gets me back to where I start. I should get 0, but this says I don't. The only way we can make sense of this is to say that induced fields are not conservative. Electrostatic fields are conservative. This expression is absolutely true for electrostatic fields. A charge sitting out there by its lonesome, or even with all of its friends, absolutely produces a conservative electric field. But these fields, these induced fields, don't come exactly from a charge. They arise from moving charges. They arrive, it's an electrodynamic field. They arrive from current, arise from currents. Turns out these guys are just a completely different animal than the electric fields we've seen. They act similarly, they obey a lot of the same laws, but this is a big law and they definitely don't obey this one. They're non-conservative. Therefore, work is done, right? That's the whole, where we started the whole thing. An induced EMF that moves charges around a coil, there's work being done. For a normal electric field, moving a charge from one point back to where it started, there's no work being done. But induced EMFs take work. Have any of you ever cranked a hand generator, either a toy generator or something like that, right? It's hard, right? It takes work. And that's not an accident, and that's not a trivial comparison. Like as the more you crank, the harder it gets to do. If you find sort of camping generators that you can charge your phone right there, hand crank, it takes a lot. Have you ever been to the McWayne Center in if you haven't, go. It's fantastic. It's designed for kids, but I freaking love it, right? I'm throwing my kids off the demo. It's like, this is cool, right? They have a demo there which my kids like to do. It's a bicycle pedal wheel that you can light up a stoplight with. It's a lot of work. There's a lot of resistance. And this is why. It actually takes energy out of the system because this sort of electric field is not conservative. It's why your batteries drain when you're running a motor, right? It takes work to keep the thing moving. So this is just, there's not a whole lot of calculation to do with this, but if you're talking about straight physics, this is incredibly important. The electric field induced by a changing magnetic flux is a completely different animal than the electric field arising from static charges, even though it has the same units, behaves similarly when it exists in space. But it is different. It's a conservative field. This would be as weird as saying that I do work against gravity when I move my feet around, right? That's probably instinctual to most of us say, well, if it gets back to where it started, there's no work done. If gravity worked like this, there would be work done, right? So this is something like a friction loop, or at least analogous to it. So to make this really true, just subscript this with induced, right? There is work being done. Where the electrostatic fields are not. Okay? Questions about any of that? Anytime you hear the word conservative in a physics class, pay attention. It's very important. Okay. Any questions on anything we've done? Any of this magnetic induction stuff? Alright, I'm going to give you something to work on while I set up the demo. Again, you can work in groups or not. Case may be. As you please. But take a background field. Let's have it going into the board. And I'm only going to draw it, obviously, in certain regions. And that's, a lot of times you say, oh, I'm only drawing it here, but it feels everywhere. But this is not that way. This field, we're going to let be confined to this region. So basically, from here to here, there's a field. Outside, there's no field. And I'm going to take a plate, right? Now, this is a plate, not a wire. Turns out, doesn't really matter. You're going to get the same sort of effect. But we're going to let this plate move into, let me draw it a little farther out. Move into this magnetic field. So I'm going to draw it in different positions. This one is not in. This one is halfway in. This one is completely in. These are all moving to the right. This one is out, or sorry, halfway out, and then it's completely out. I want you to, in each of these situations, determine the force, the direction of the force, I should say. You don't have enough to give you the magnitude. The direction of the force acting on the plate as it moves through the magnetic field. Now, to get you started, like I said, this is going to work very similar to how a wire would work. What you're going to do is you're going to set up what are called eddy currents that will flow in one direction or the other around the rim of this plate of metal, right? And I do want you to imagine that it's a solid plate as it's moving through. So work it like you would work just a square loop of wire. Figure out the directions of the currents using Lenz's law, and then figure out the forces using the right-hand rule for forces of magnetic fields on currents. Noticing that in some positions, some side of it is in the field and some side of it's not. Y'all work on that for a few minutes while I set up this demo. Which, spoiler alert, is this actual situation.
EMF said 0 here, 0 here.
So if your magnetic field's going into the page and the sheet is moving that way, that means its force is that way. So it means its current is wanting to flow that way, and the EMF wants to oppose it, so the current's going to flow that way.
Okay, so I won't do that. It's going up.
So the thing is moving that way,
Yeah,
right? So that means the force is that way. The magnetic field is going into the page. So that means its direction of current is going to be going above. So for EMF, you have to flip it.
Okay. For some reason I thought it was down because of like the way they explained it here.
How are we doing? Let's work on it. Alright.
Could be totally
I have 5 positions. What is the only way, or I should say, what are the conditions under which we're going to induce a current in this plate? What has to be happening? Flux has to be changing, right? The flux through that area has to be changing. So let's take care of the easy ones first of all. Is there a change in flux in this position? There's no field. No, we can even go backwards to that. The first question we ask ourselves is there a flux, right? Is there a flux through this field or through this plate? No, because there's no field. So if there's no flux, it can't be changing, so there's no force here. 0 force. What about this position? Is there a flux through this position? No. What about this position? Is there a flux through the plate? Yes. Is it changing? No. The plate is completely encased in the magnetic field, assuming that the magnetic field is constant. Right? There's no change in flux as it passes through. As long as it's completely enclosed, no change. So it turns out there's no induced current here either, right? So you go through that process. First question we ask ourselves, is there flux? The answer here is no, so we're done. The answer here is yes, there is flux. But now we ask ourselves, is it changing? No, we're done. All right. This position, is there flux through the area here? Yes. Is it changing? Yes, right? Because we're entering the field. Now we ask ourselves the other question, increasing or decreasing? Increasing. What does nature want to do? Decreases, right? So now we have to look at the direction of the field. It's into the page. So I know that nature wants to decrease it. The field is into the page. How is she going to induce the field to decrease it? She's going to have to induce one pointed out of the page. So the induced field needs to look like this, right? Because nature wants to decrease what's happening. And the vector sum of those two is less than the larger one. Alright, use your right hand rule for fields. What direction of current is needed to produce that field? Remember, thumb goes into what's straight. In this case, that's the field. Fingers tell you what's curved. Counterclockwise is what I get. Thumb goes into the direction of the field. Fingers then tell me the direction of the current. I get counterclockwise. So there's going to be a current that gets set up in this plate that rotates, that goes like that, that flows like that. Okay. Alright, so let's now look at the forces, because that's what I've asked you about, right? Let's look at the forces on this. Okay. Well, it's not completely enclosed in the magnetic field. Do we all agree with that? This portion of the current is in the field. This portion is not. Therefore, the net force is not 0. That's one of our axioms, right? Net force on a loop of current enclosed in a magnetic field is always 0. This isn't enclosed. This one is, right? But we already figured out that this is 0. We didn't even have to get there. There's no current there anyway, so there's not.